All right, so starting from the very beginning, if you remember cases and variables, a case is an experimental unit from which data are collected, and a variable is a characteristic that is measured and it can take on different values. So really just anything that can vary. So if you're thinking about if a college professor wants to know if the students who get more sleep at night get higher homework and exam grades, in this example here, the students are the cases, and then the variables are the homework and the exam grades. So categorical and quantitative variables. So categorical variables are names or labels. So anything with really a category. They can either have a logical order or no logical order, and usually these are qualitative variables. On the other hand, quantitative variables have numerical values with magnitudes that can be placed in a meaningful order with consistent intervals. So we can break quantitative variables down into either discrete or continuous variables. So a discrete quantitative variable is a set value. So if you were saying the number of children in a household, that would be a discrete quantitative variable because there's a set value of number of children. While a continuous quantitative variable has a value between values. So that would be, if you're thinking of mostly things that can be measured, such as distance traveled or height, weight, things of that nature. So explanatory and response variables, they're also known as independent and dependent variables. So an explanatory variable, that's what we call an independent variable as well. It explains variations in the response variable in an experimental study. While the response variable is what we measure, so that is the outcome that is measured following the manipulation of the explanatory variable. So for example, how does sleep at night affect your exam grades? So sleep at night, that can be manipulated, that can be our explanatory variable. And then our exam grade is what we're measuring as a result of how much sleep you get at night. So here's just a breakdown of some of the symbols you have seen. These are the most common ones, I think: mean, proportion, and correlation. So just the difference between the population parameter and the sample statistic. I know I've gotten a lot of just some questions throughout the semester just about clarifying the symbols because there's a lot of symbols to keep up with. So here's just a little chart of what symbols you need to know for the population parameters and the sample statistic, because when you're writing hypotheses for hypothesis tests, you need to use the population parameter. You want to make sure that you don't get those confused with sample statistic symbols. And then just know that your statistic is a measure concerning a sample, and then your parameter is the measure concerning a population. And for statistics, we really we want to use our statistics in order to make an inference about the population as a whole, and we call that inferential statistics. So non-response and response bias are two ways to measure a certain type of bias. They seem very similar, but they actually are very different from one another. So I'll start with response bias because I think that's more clear. So response bias is when you favor certain outcomes that occurs when participants do not respond truthfully. So this response may be in order to align with social norms or to appease the researcher. So an example I like to use for this question is if a teacher wanted to gather information on her students. So if she asked her students to take a survey, and one of the questions asked if they have ever cheated on homework or a test, a lot of the students would probably say that they never have, even if they have or even if they haven't. But that is response bias. So they are saying that if they have, they are saying that they haven't because they want to appease their teacher, and it's kind of skewing the data because they're not telling the truth. Back up to non-response bias. Non-response bias is when you favor certain outcomes that occurs when the individuals who choose to participate differ from the individuals who choose not to participate in the study. So an example of non-response bias is below. A restaurant invited their recent customers to complete an online survey. Customers who had really strong feelings about their experience, either positive or negative, were very likely to complete the survey, while customers who had a neutral experience were much less likely to complete the survey. So I like this example because it really relates to real life if you think about it. If you were to go to a restaurant and have a really great experience, you would be more inclined to complete the survey in order to share that with the restaurant and potentially share that to other customers. Or on the other hand, if you had a very negative experience, you wanted to give the restaurant feedback in order to improve, you would most likely complete the survey. But if you had a neutral experience, it didn't really stick out to you, you probably wouldn't even think twice about completing the survey. So experimental and observational studies have come up a lot. So we'll start with experimental study. An experimental study is a study in which the researcher manipulates the treatments received by the subjects. The difference between an experimental and an observational study is that an experimental study has manipulations and the observational study does not have manipulations. So observational studies are left completely up to nature. They're pretty much just observational. You're just observing the whatever you're testing, and you're not making any manipulations to it. So you leave it completely up to nature. So one problem with observational studies is that they do not take confounding variables into account. So confounding variables, also known as third or lurking variables, they vary between cases, and they're mostly related to both the explanatory and response variables. So very common confounding variables, age. Age is a very common confounding variable because it's a lot of times when you collect data, you may not take age of your participants into account, and you may see a pattern among people of a certain age, and then you may not realize that that has directly has to do with that confounding variable. So we're going to look at independent groups and paired groups. So to start with independent groups are cases in each group that are unrelated to one another. So if you're looking at a t-shirt company that studies how many t-shirts American men and women own, if they take a random sample of 1,000 American adults, and if they ask each individual if they identify as a man or woman, how many t-shirts they own. The number of t-shirts a man owns will not affect the number of t-shirts that a woman owns. That's why these are independent groups of one another. While paired groups, these are cases in each group that are some way matched with one another. So we also call this dependent samples or matched pairs. So an instructor wants to compare students' scores in the midterm and final. She obtains a sample of students and then records each student's midterm exam score and final exam score. So these are paired groups because each student has scores that are matched with one another. So their midterm and final exam score are matched, and then they compare them because your midterm exam score may affect your final exam score. All right, so moving on to blinding. So blinding is used to avoid bias. So we have two types of blinding that we can use. So we can have a single blind study or a double blind study. A single blind study is a study in which the participants do not know the treatment they have been assigned to, but the researchers do. While in a double blind study, neither the participants nor the researchers know which case is assigned to each treatment. So it really just, in both studies, the participants do not know which treatment they're given, but the difference here is whether the researchers know which case is assigned to each treatment. Sometimes in studies, you'll have a control group. So this is the group that is just kept constant the entire time, so it does not receive the actual treatment. So they may receive a placebo sometimes, or they may not receive anything at all. So just a reminder, placebo is just something that appears to the participants to be an active treatment, but it doesn't actually contain active treatment. So this could be a sugar pill or something along those lines. Okay, so on to the first review of lesson 1. A school psychologist wants to use students' intelligence test scores to predict their reading comprehension scores. She takes a sample of 100 students and records each individual's intelligence test and reading comprehension scores. Here, what is the explanatory variable? So you can type your answer into the chat box and then we'll go over it. All right, great. Everybody got this one right. The answer is B. So here, intelligence test scores is our explanatory variable. Here, if we were looking for the response variable, it would be reading comprehension scores because that's what we want to predict. Okay, so we're done with lesson 1. Now we're on to lesson 2. So we're going to start with one categorical variable. So data concerning one categorical variable can be summarized using a proportion. So just going over how to calculate a proportion, it's the number in the category divided by the total number. So the symbol for a sample proportion we went over in lesson 1 is p hat, and then the symbol for the population proportion is p. And just one last thing, a proportion must be between 0 and 1 at all times. Sometimes if you see something in a percentage form, just make sure that you keep in mind that that can be converted to a decimal, and it's between 0 and 100. Okay, so risk and odds, I kind of combine them onto the same slide because you can kind of compare them to one another. Oops. So risk is the probability that an event will occur. So you can see this in a decimal or a fraction or a percentage. You can calculate risk by taking the number with an outcome divided by the total number of outcomes. So if we talk about flu risk as an example, if we say 45 out of 100 children get the flu each year, we can calculate the risk of a child getting the flu. So we can calculate that risk by taking 45 out of 100, and that can be equal to 0.45 or 45%. And then we can just say that 45% of children get the flu each year. Finally, with odds, we can say we use odds to compare the likelihood of an event happening with the likelihood that an event will not happen. So we can calculate odds by taking the number with the outcome divided by the number without the outcome. That's one way to calculate it. Another way to calculate it is if you already have a calculation for risk, you can use that to calculate your odds. So you can use your risk by doing that risk over 1 minus risk. And that's exactly what we're going to do right now to calculate the odds using the flu risk that we calculated before. So we would take 0.45 divided by 1 minus 0.45. And then we get 0.45 divided by 0.55. And then once we do that out, we get 0.818. We can conclude that by saying that the odds of a child getting the flu is 0.818 to 1. So now we're just going to go over some visual representations you might see. So these visual representations I'm going to show you in this slide and the next few slides, they all have the same data, just Penn State Math Club for University Park. It just shows the number of students in the club and then the ages. So we have a pie chart on the left, a frequency table on the right. Here is a bar chart. And then if we wanted to divide this up even more, if we wanted to add another categorical variable to this data, we could do two-way table. So a two-way table is for two categorical variables. So here we have class standing and gender, males and females. And we can just represent this data in a two-way table. It looks very nice, you can tell. But this is a good thing to know that for a two-way table, you will use two categorical variables. For the previous one, you can see that we have two quantitative variables. Okay, so moving on to probability. So probability is the probability that an event will occur. So the calculation for this is a little similar to proportion you may see. It's the number in group A divided by the total number. And the range of probabilities will range from 0 to 1. If you get 0 as your probability, which most likely will not happen, but that means that your probability of your event happening is 0. It is impossible. There's no way that your event can occur. An example of this would be the probability of rolling an 8 on a 6-sided die. There's only 6 sides to a 6-sided die, so there's no way you could roll an 8. That probability would be 0. On the other hand, if you were to get a probability of 1, that means that event is certain to occur. Okay, so disjoint independent events. So a disjoint event is an event that never occurs at the same time. So I like to use an example here for class standing. So typically you'll have freshman, sophomore, junior, senior. you cannot be a freshman and a sophomore at the same time. They are mutually exclusive events. Moving on to the Venn diagram. The Venn diagram, you've probably heard of this term before, but it's a little different in the way we use it in statistics. So Venn diagram is a visual representation. So you see on the right, I kind of drew out a Venn diagram there, but the sample space is depicted as the green box. So that is our sample space. And events in the box are represented as circles. So each event, A and B, those are both events that occur in the sample space. So moving on to independent events, these are unrelated. So the outcome of one event does not affect the outcome of another event. So for example, if we went over the t-shirt example for the number of t-shirts that men own, do not affect the number of t-shirts that women own in a certain company. And just combination events, these are good things to know for the final exam. So intersection, union, complement, and conditional. So intersection is the probability of A and B occurring. So they must occur. Union is a little similar to intersection, but it has a little tweak to it. It's a little different. So it's a probability of A or B occurring. So A can occur, B can occur. If A and B both occur, this is included in the definition of a union. Complement is the probability of not A occurring. And then conditional is the probability of A given B. So something happening as a result of something else occurring. All right, so outliers, you guys are probably familiar with outliers by now. So they are one or more observations within a set of data that may fall outside the general scope of other observations. So you can identify outliers on dot plot, histogram. They are really prevalent on box plots, you can see. But here in the scatter plot below, you can see that there's an outlier, probably, I'm not sure what number that is, probably 75. But that is outside the general scope of the observations. You could even vouch that the next number to that 70s number is an outlier as well. So moving on to shape, symmetrical normal distribution, you guys are definitely familiar with those. Symmetrical distribution is a distribution that is similar on both sides of the center. A normal distribution is a type of symmetrical distribution, but it's bell-shaped, and the mean of a normal distribution is 0, as well as having a standard deviation of 1. So now we're going to move on to skewness. So left skewed and right skewed. So it's just if variables are more spread out on one side of the center than the other. So in a left skewed distribution, you'll have all your data piling up on the right side, and you'll see that there's not much in the left. That's why it's called left skewed. And then in a right skewed distribution, a lot of the data will pile up on the left side, and you'll have it a skewness on the right. So mean, median, and mode are 3 measures of central tendency you guys definitely want to know. You're probably most familiar with the mean, which is the average. So we've used it a lot. X bar, mu, our sample in our population. The formula for mean, if you have to calculate it, is the sum of all of your x's divided by the number of values, or the number of x's you have. Your median is the middle of the distribution that has been ordered from smallest value to largest value. If you have a distribution with an even number of values, then you will take the mean of the middle 2 values. So you'll just add those 2 up and then divide by 2, and that will be your median. And then finally, the mode is the most frequently occurring value or values in the distribution. So a mode could be quantitative or categorical. A lot of people just assume that mode is a quantitative variable, but it could be categorical as well. If it was categorical, it would just be the category or label that's most common. So here's just how skewness can affect the measures of central tendency. So it shows how, whether you have symmetrical data, left skewed or right skewed, how the mean, median, and mode relate to each other. So I think this is a really good chart to know for the final exam. Yeah. I'll just leave it there. All right, so the empirical rule is a statement about normal distribution. So the paragraph in the second bullet is just a description of the image on the right. So on a normal distribution, about 68% of data will fall within 1 standard deviation of the mean. About 95% will be within 2 standard deviations of the mean, and about 99.7% will be within 3 standard deviations of the mean. The 95% rule is just a shortened version of an empirical rule, so it really just talks about the middle 95% of data. So the 95% rule states that approximately 95% of observations fall within 2 standard deviations of the mean on a normal distribution. Okay, so that was a lot of information, but we're going to do a review. So the average weight of a female border collie is 45 pounds with a standard deviation of 4 pounds. What is the z-score for a female border collie that weighs 51 pounds? Okay, so I'm going to go over the answer. You guys, those of you who answered got it right, is B. So here we take our x minus our x bar, 51 minus 45, divide that by our standard deviation of 4, and then we get 1.5 as our z-score. So great job. So we're going to talk about percentiles. So percentiles is just the proportion of a distribution less than a given value. So it's really just a statistical measure of distribution. So I just have 2 examples of percentiles when you're talking about like test scores, for example. I think that's the most relatable example. So if a student scores in the 90th percentile in a test, then he or she scored better than 90% of students who took the test. So that's very good. Same example, if a student scores in the 70th percentile on a test, then he or she scored better than 70% of students who took the test. So the 5-number summary is definitely important to know. It consists of 5 numbers, minimum, Q1, median, Q3, and your maximum. So just a reminder that Q1 is the first quartile, it's the 25th percentile. Q3 is the third quartile, 75th percentile. So you'll want to know how to compute range and IQR. So range is the difference between the maximum and the minimum, and then IQR is the difference between the third quartile and the first quartile. So range you can calculate by taking max minus min, and then the IQR you can calculate by taking Q3 minus Q1. So here I'm asking you to calculate the range according to the 5-number summary. Oops, I'm sorry. I just clicked on the answer by accident, but for those of you that answered, the answer is 24. Maximum minus minimum is how we calculate the range. Our maximum is the fifth number in the five-number summary of 98, and then our minimum is the first number in the five-number summary of 74. And once we subtract those, we get 24 as the difference. Okay, so now we're moving on to lesson 3. So here is a single box plot example. So I really like this chart because if you're having trouble with the single box plot, you can kind of look at it and it breaks down each part of the box plot and just what each part means. So there's a way to identify outliers without having to look at a data set or a graph. So we can actually just use math to calculate this. So we will calculate a lower fence and an upper fence. And these kind of act as barriers. So any observation that is below the lower fence or above the upper fence, that would be considered an outlier. So we use Q1 and Q3 and our IQR in order to calculate the lower and upper fences. So here, we're going to identify the five-number summary here in the data. And we're going to use that five-number summary in order to see if there's any outliers present. So we calculate our IQR here of 90 minus 80, it's 10. Then we first are going to calculate our lower fence. So we take Q1, which is 80, and subtract 1.5 times 10, which is our IQR, and we get a lower fence of 65. Next, calculate our upper fence. We take our Q3, which is 90, and add that to 1.5 times 10, which is our IQR, and we get 105 as our upper fence. So now that we have our lower and upper fences calculated, we can say that any scores below the lower fence of 65 and above the upper fence of 105 are outliers. So here's our data set again. So looking at this data, there are no outliers present because you can see, luckily the data is in order from lowest to smallest, so it's pretty easy to identify if there are outliers or not. But our lowest value here is 74, and our highest value is 98. So they don't go below our lower fence or above our upper fence, so that means that there are no outliers present in this data. All right, so scatter plots are used to show the relationship between the explanatory and response variables. So just the definition of a scatter plot, it's a graphical representation of two quantitative variables in which the explanatory variables on the x-axis and the response variables on the y-axis. So just 4 things to consider when you're examining a scatter plot. What direction is it going in? Is it positive or negative? Is it linear? Is it nonlinear? How strong are the relationship between the two variables that you're looking at? And then consider if there are any outliers present. All right, so according to the box plot, which of the following is approximately represented by a score of 565? All right, great. Our answer here is B. So just going through A through C, Q1 would be represented by the first line here on the box. That would be around maybe 505. Q3 here is approximately represented by a score of 565. It is the top line in the box. And then the median here is just represented by the middle line in our blue box. probably around 530. So if you were having trouble with that question, you can always go back to the first slide that shows an example of a box plot, and that's where you can see how these all line up. Which of the following values of R could be used to describe a very weak positive association between two variables? So this is all about correlation here. All right, there were some mixed reviews on this question, but the majority of you said C, which is the correct answer. You just want to be careful here, making sure that you read the question. There's two key factors you want to look out for, weak and positive. So that's what you're looking for. So you want to make sure that your number is positive first off, and then from there, out of the positive numbers, you just pick the one with the lowest correlation. So yes, B. Yes, B is negative, so you automatically, I know the mind just goes right to negative is like weaker, but actually that 0.9 would be a very strong negative association. So, okay, so we're cruising here on lesson 4 already. What is a confidence interval? Oh, okay. So a confidence interval, you guys definitely know this by now. You've done a lot of confidence intervals, but it's a range computed using sample statistics in order to estimate the population parameter given a stated level of confidence. So through these, you use your sample distributions. Make sure that your sample distribution has a mean approximately equal to the mean in the original distribution, and your standard deviation known as your standard error. Okay, so here's just a overview of confidence intervals. So the formula for confidence interval is your sample statistic plus or minus margin of error. Margin of error can further be broken down into your multiplier times the standard error. So the margin of error depends on two factors. So first off, it depends on the level of confidence. This level of confidence ultimately determines the multiplier. So we can get your multiplier from the empirical rule, pretty much. So it's from that distribution on the left. Based on whichever level of confidence you have, that will affect your multiplier. So most commonly you see a 95% confidence interval, and since 95% of the distribution is within 2 standard deviations of the mean, we typically use we always use 2 as our multiplier for 95% confidence interval. And then second factor of margin of error is the value of the standard error, because that's what you multiply to the multiplier, and that's how you reach your margin of error. And then at the bottom, that just shows the form for a 95% confidence interval. It's the same formula as the original confidence interval formula at the top. It just already has the multiplier of 2 in there. Okay, so on to bootstrapping. So bootstrapping is a resampling procedure that uses data from one sample in order to generate a sampling distribution by repeatedly taking random samples from the known sample. So in bootstrapping, we call this as sampling with replacement, because you put each set of data or each value back into the original set of data, and it has an equal chance of being selected again. So here's an example of bootstrapping. So we have data concerning the mean heights, or the heights of individuals in a random sample of 15. To construct a bootstrap distribution for the mean height, we would first randomly select one individual from that sample and record their height. Then with that individual placed back into the sample, we would again randomly select a second individual and record their height. So this is known as sampling with replacement because we put each case back into the sample after recording the height. So we repeat this process until we have selected 15 values, and then we would use those 15 values to compute a bootstrap sample mean. So we can do this as many times as we want. So just things to make sure you notice is that individuals may appear in the bootstrap sample more than once. They could even occur every single time if you really could. It's probably unlikely, but it could. And then also the distribution of bootstrap sample mean is what we call the bootstrap distribution or the bootstrap sampling distribution. So just thinking about sampling with replacement, I like to think about if you were to take a bunch of marbles out of a hat, record which color, for example, you took down, and then put that marble back in the hat. It has just as equal chance of being selected as the other ones do as well. So now we're just going to check out the impact of sample size on confidence intervals. So as your sample size increases, your standard error decreases. So that means that there is an inverse relationship between sample size and standard error. Vice versa, as sample size decreases, your standard error will increase. So just an illustration of this relationship below in the distributions, you can see that the sample size is larger in the sampling distribution on the right than it is on the left. And you can just see, first off, in the top right corner, it does say standard error. So you can see that they are notably different in each distribution. But just looking at the distribution itself, you can see how much more varied it is in the first distribution on the left than it is on the right. So that means since it has a higher variance on the left, it has a higher standard error. Okay, we're on to lesson 5 now. So lesson 5 is an introduction to hypothesis testing. So before we were using confidence intervals to estimate unknown population parameters. So hypothesis testing is really just a more formal method to test whether a given value is a reasonable value of a population parameter. So in hypothesis testing, we compute the probability that a population with a specified parameter would produce a sample statistic as extreme or more extreme to the one we observed in our sample. So this probability is known as the p-value, which we use to estimate statistical significance. So statistical significance is really just stating whether or not our data we observed is due to actual differences in the population. So we're going to go through the 5-step hypothesis testing procedure now. This process will be repeated a lot in this lesson, so I'm going to go over it most specifically now. I will definitely emphasize where they are different, mostly in step 1 throughout the lesson though. So step 1 in hypothesis testing is to write your hypothesis statements. So each test has a null and an alternative hypothesis. So your null hypothesis states that there is not a difference in the population, while your alternative hypothesis states that there is a difference in the population. So there are 3 things to know when you're writing the hypotheses. You need to know the parameter you're testing, whether it's single proportion, single mean, correlation, the direction of your test, whether it's non-directional, right-tailed, or left-tailed, and then the value of the hypothesized parameter, so which number that goes into the hypothesized statements. And then just make sure you always write your hypotheses in terms of population parameters. So if you're writing a proportion, you always write in p, not p hat, or in a mean, you write in terms of mu and not x bar. So randomization procedures. So for the randomization distribution for a null hypothesis, we construct them given that the null hypothesis is true. And we use these distributions in order to find the p-value. So once you find the p-value, you can decide whether to reject or fail to reject the null hypothesis. Just to review, make sure that you never accept the null hypothesis, and you always want to conclude in terms of the null hypothesis and not the alternative hypothesis. So you either reject or fail to reject the null hypothesis. So you reject the null hypothesis if your p-value is less than or equal to alpha, and then you fail to reject the null hypothesis if your p-value is greater than alpha. So this is just a refresher. I just went over the p-value. So when you fail to reject the null hypothesis, when your p-value is greater than alpha, you're basically saying that there is no sufficient evidence to say that there is something going on here in your data. On the other hand, if your p-value is less than or equal to alpha, then we can reject the null hypothesis and conclude that there is a difference in the population. And make sure you note that your alpha is always 0.05 unless otherwise stated in the problem that you're working on. Okay, so do the majority of all World Campus .200 students own a cat? What is the correct alternative hypothesis for this research question? All right, awesome. You all got the answer C. Oops, sorry. P is greater than 0.50. Here in this case, if we're looking for the null hypothesis, that would be B. All right, on to the next question. We use Stacky to construct a sampling distribution based on a research question. We get a p-value of 0.49. What is our first conclusion in terms of hypotheses? All right, yeah, so here our answer is C. By accident, I put A as the answer, but I don't want to confuse you guys, but you all got it right. The answer is C here. We have a p-value of 0.49. That is definitely greater than 0.050. So that we should fail to reject the null hypothesis. Our data is not statistically significant. All right, let me clear this. Is the mean height in the population of all World Campus .200 students different from 65 inches? What will we use in this scenario? All right, great job. Hypothesis testing for a single mean is our answer here. So mean height, that kind of gives away that we're looking for the single mean. And then hypothesis testing, we have a research question here, so that's why we're going to use hypothesis testing. You can easily make your hypotheses because it's looking to see if the World Campus Stat 200 students are different from 65 inches. So great job there on that question. All right, we're on lesson 6 already. Wow. Okay. Type 1 and type 2 errors. All right. So when you're conducting a hypothesis test, there are 2 possible decisions that you can make. So you can either reject the null hypothesis or fail to reject the null hypothesis. So in most cases, we actually do not know whether our inference is correct or incorrect. So we really don't know after we reject or fail to reject whether that was the right decision or not. So if you reject the null hypothesis, 2 things could happen. There could really be a difference in the population, so that would be the correct decision, or there is not a difference in the population, but our sample just happened to be different. So that means an error was made. On the other hand, if you fail to reject the null hypothesis, you could either, the null hypothesis is actually really true and there's no difference in the population, which is the correct decision, or there actually is a difference in the population, but we failed to reject it, so an error was made. So this is where type 1 and type 2 errors come into play. So rejecting the null hypothesis when the null hypothesis is really true is a type 1 error. So this is denoted by alpha, and alpha is just the probability of a type 1 error. A type 2 error is when you fail to reject the null hypothesis when the null hypothesis is really false. So this is denoted by beta, and beta is just the probability of a type 2 error. So in the chart there, it shows what your decision is based on what is actually true in reality. So there are 2 options. So it'll either be correct or there will be an error. So for each decision, there is a certain error and a certain correct decision. And if your decision matches up with what is true with reality, that will be correct. But if your decision does not match up with reality, then there will be an error that is made. So an example I like to use to put type 1 and type 2 errors in perspective is this trial example. So a man goes to trial where he is tried for stealing from a store. So the hypotheses tested are the null hypothesis is that he is not guilty, and the alternative hypothesis is that he is guilty. So a type 1 error is committed if we reject the null hypothesis when the null hypothesis is true. So in this case, it means that the man did not steal from the store, but he is found guilty and is punished for a crime that he did not commit. On the other hand, a type 2 error is committed if we fail to reject the null hypothesis when it is actually false. So in this case, it means that the man actually did steal from the store, but he is found not guilty, and he is not punished for a crime that he actually did commit. So I hope that helps you, if you're having trouble with that, see the underlying differences between type 1 and type 2 error. All right, so power is the probability of rejecting the null hypothesis given that the null hypothesis is false. So it's a little wordy, but it's the probability of correctly rejecting the null hypothesis. So you can calculate power by taking 1 minus beta. And remember, beta is just the probability of committing a type 2 error. Okay, a group of culinary arts students is comparing 2 methods for preparing asparagus, traditional steaming and a new frying method. They want to know if patrons of their school restaurant prefer the new frying method over the traditional steaming method. A sample of people are given asparagus prepared using each method and asked to select their preference. A statistical analysis is performed to determine if more than 50% of participants prefer the new frying method. So here our null hypothesis is p equals 0.50, and our alternative hypothesis is p is greater than 0.50. Which of the following is true? Okay, so the answer here is B. Oh, no. The answer is definitely not B. Sorry. The answer is C. I apologize. My slides got all messed up. But the answer is C, not B. Um, this is not a left tail test. This is actually a right tail test. Um, and there is not a type 1 error present. We actually don't even know if there's a type 1 error present because we haven't made a decision about our data yet. So once we make a decision and we know what the actual reality was, then we can determine whether or not there was a type 1 error present. And population proportion is being tested because we have P in our null alternative hypotheses here. So I apologize for that confusion, but the answer there is C. So moving on to the next question. In the last question, we say that we should reject the null hypothesis. Suppose we reject the null hypothesis, but actually the patrons of the school restaurant do not prefer the new frying method over the old frying method. Which of the following is true? Alright, our answer here is A. There is a type 1 error present because if we reject the null hypothesis, we see that there is something going on, there is a difference in our data, but actually the people at the restaurant do not prefer it, so there really was nothing going on even though we said there was, so this is a type 1 error. Alright, we're halfway there, on to lesson 7, common distribution. So you guys know about the normal distribution. It's the bell-shaped distribution. It has a mean of 0 and a standard deviation of 1. It's also known as the z-distribution, and 100% of observations fall under this curve. So the central limit theorem states that if your sample size is sufficiently large, then the sampling distribution will be approximately normally distributed. So the standardized score, or z-score, is known as the distance between an individual score and the mean in standard deviation units. So using the normal distribution for hypothesis testing, we use the same 5-step hypothesis testing procedure. So we're going to check our assumptions and write our hypotheses. Then we're going to calculate a test statistic, then determine the p-value, make a decision, and then state our real-world conclusion. So for the standard normal distribution method, when we're using this method, the test statistic is the standardized value, that is the boundary of the p-value, So for a z-score, we calculate that by taking x minus x bar and divide that by the standard deviation. When we're conducting a hypothesis test, the sampling distribution is centered on the null parameter, and the standard deviation is known as the standard error. So for a test statistic, we can calculate our test statistic by taking the sample statistic minus the null parameter, which is the number in the null hypothesis, and then divide that by the standard error. So confidence intervals, the general form of confidence interval you remember is the sample statistic plus or minus z star times the standard error. So things to remember here is that the mean is equal to the sample statistic and the standard deviation is equal to the standard error. Your z-star multiplier can be found on the z-distribution as well. So switching gears a little bit into binomial probabilities. So a binomial random variable is a specific type of discrete random variable that counts how often a particular event occurs in a fixed number of tries or trials. So for a variable to be binomial random variable, it must meet 3 conditions. So first, there must be a fixed number of trials or a fixed sample size. Second, the probability of success must be the same for each trial. And third, the trials must be independent of one another. So if you think of the example of the number of tails you get when you're flipping a coin 10 times, this is a binomial random variable because it does meet all of the conditions. So there are a fixed number of trials. For this example, we have 10 trials. The probability of success is the same for each trial because heads or tails, it will always be equal 50%. And the trials are independent of one another. So whether you get heads on one trial or tails on another, it does not affect whether or not you'll get heads or tails on the next one. So here's just a way to calculate mean and standard deviation for binomial probabilities. So the mean of a binomial random variable is calculated by your sample size times the probability. And then the standard deviation is calculated by the square root of n times p times 1 minus p. Okay, so for the SAT math scores, you have 500 as your mean and 100 as your standard error. Let's apply the empirical rule to determine the SAT math scores that separate the middle 95% of scores. All right, so our answer here is B. Here we're just really calculating using the confidence interval formula for this question. So we need 3 pieces of data to answer it. So we need our mean, our multiplier, and our standard error. So we already have the mean and the standard error given. The mean is 500 and the standard error is 100. Finally, we just need the multiplier. So since we're using the empirical rule and we're looking for the middle 95% of scores, since 95% of scores would be within 2 standard deviations of the mean, we will use 2 as our multiplier. So here, I think I wrote it down. Yeah, so we're going to calculate 500 plus or minus 2 times 100. Once we multiply out 2 and 100, we get 200 as our margin of error. And then once we add and subtract that to 500, we get 300 and 700 as our final answer. So which of the following is not an example of a binomial random variable? All right, our answer here is B. So just going through those three conditions that we have to meet for a binomial random variable. Um, B, all of them do follow them, the conditions except for B. So there are a fixed number of trials of 20. The trials are independent of one another because the result of one lottery ticket does not the effect of the result of another lottery ticket. But the probability of success is not the same for each trial, since we have different kinds of lottery tickets, and the chance of winning for each would be different. So, all right, lesson 8 is inference for one sample. So here, lesson 8 and 9, they kind of start to get a little repetitive here. So I'm going to go through it as smoothly as possible, I hope. But if you have any questions along the way, just let me know. So for one, we're going to start with one sample proportion. So according to the rule of sample proportions, if our assumptions are met and our proportion is bigger, proportion and our sample size multiplied together is greater than or equal to 10, otherwise saying if we have at least 10 successes and 10 failures, then our sampling distribution will be approximately normally distributed. So if all of our assumptions are met, then we'll have the standard error of the square root of the proportion times 1 minus the proportion divided by the sample size. So we would use the normal approximation method. So if our assumptions are not met, then we would use the binomial distribution. So for one sample proportion of confidence intervals, we want to make sure that we calculate the number of successes and number of failures in our sample, and we want to make sure that each of those numbers is at least 10. Once we pass that, we can calculate our confidence interval. So our confidence interval is the p hat plus or minus z star multiplied by our standard error, which was given in the previous slide, but it's given again here. So just remember that the value of the z-star multiplier depends on our level of confidence, and the standard error is computed using p hat as an estimate of p. So we can start with the confidence level and margin of error in order to determine a minimum sample size needed to produce these results. So this is really just kind of, I think about it as like working backwards, computing a sample size needed in order to produce a margin of error that matches a certain confidence level. So we can use this formula in order to calculate our sample size in order to estimate a population proportion given a margin of error and confidence level. So if we do not know the estimated value of our proportion, we can use 0.50 because it provides a very conservative estimate and it's the largest sample size calculation. So one sample proportion for hypothesis testing, we use one sample with one categorical variable. So the hypothesized value of the population proportion here is symbolized by p sub 0 because this is the value in the null hypothesis. So we want to make sure that we have at least 10 successes and 10 failures again for our hypothesis testing, and then we have a similar standard deviation formula, except where we had p before, we have the hypothesized value from our null hypothesis. So here's our 5-step hypothesis testing procedure. We go through the list of the 5 steps, so we check our assumptions and write our hypotheses, again making sure we have 10 successes and 10 failures. Then we calculate the test statistic. The formula for the test statistic is on the right, with the sample proportion, the hypothesized population proportion, and the sample size. Then once we have our test statistic, we can determine our p-value, and then decide whether to reject or fail to reject the null hypothesis, and then state a real-world conclusion. So moving on to one sample mean, we just did one sample proportion. For the central limit theorem, a large sample size in this case is defined as one where our sample size is greater than or equal to 30. So since we estimate our standard deviation by using S, we use the t-distribution for the sample mean instead of the z-distribution. So just remember that the t-distribution is different from the z-distribution because the t-distribution's height varies depending on sample size. So that's where degrees of freedom will come into play. So we can again compute a necessary sample size if we're given a level of confidence and a margin of error. This just differs differs a little bit because the t-distribution is different for each degree of freedom. And you just want to make sure when you calculate the sample size that you round your answer up in order to make sure that you can get that confidence level and margin of error if you were to use that sample size in the future. So here's hypothesis testing and confidence intervals for one sample mean. So for hypothesis testing, we have the same 5-step procedure that we used, that we have been using. So here are assumptions that we have to check are that our sample size is sufficiently large, so greater than or equal to 30. Then once we have that, we can calculate our test statistic. Then we can determine the p-value. So here we're going to use the t-distribution. Make sure you plug in your degrees of freedom, which is n-1, in order to find your p-value. Then we can decide whether to reject or fail to reject the null hypothesis based on our p-value. If it's less than or equal to alpha, we'll reject. If it's greater than alpha, then we'll fail to reject. And then state our real-world conclusion. Moving on to confidence intervals on the right, the confidence interval for a population mean is x bar plus or minus t star times our standard error, and our standard error for the population mean here is the standard deviation divided by the square root of the sample size. Okay, so moving on to paired means. So paired means, we went over it before, so the dependent samples. So we can go about 2 ways of collecting paired data. So it can either involve taking 2 measurements on the same subjects. So for example, the effectiveness of a diet plan. So if you wanted to test the effectiveness of a diet plan, you could weigh each participant both before and after the diet plan, then compare the data, see how much weight was lost in order to see if it was effective. And then you can, another way you can collect data through paired data is if you take 1 measurement on each of 2 related subjects. So here you're just taking 1 measurement on 2 related subjects before you're taking 2 measurements on 1 subject. So back to the 1 measurement, as long as the subjects are related to one another, so if you're studying twin pairs, husband and wife, brother and sister, any 2 subjects that are related to one another would work. So for confidence intervals for paired means, it's pretty much the same as it was before for one sample mean, so we have the same standard error. The only difference here is that we use the subscript d for our x bar and our standard deviation. That just stands for the difference, so it represents the difference between the 2 means that we'll use for our sample statistic, and if we have 2 standard deviations, we'll find the difference between those and use that. Just a note that for t-star, you want to make sure that you use your multiplier with the degrees of freedom of n-1. Hypothesis testing is a little more lengthy for paired means. Calculating the test statistic is a little bit more, so just going off from 1 to 5, so you're going to check your assumptions and write your hypotheses. In terms of assumptions, you want to make sure that your data is paired and that your sample size is at least 30. So calculating the test statistic, it is similar to the general formula that we have been using. I have it on the right there. You're going to want to make sure that you calculate your standard deviation and your observed sample mean difference before you calculate your test statistic. Those 2 formulas are below the test statistic formula. So once you calculate your test statistic, you're going to want to determine the p-value. So in order to determine the p-value, you're going to plug your test statistic into the t-distribution with the degrees of freedom of n-1. And then you're going to decide whether to reject or fail to reject the null hypothesis, and then state our real-world conclusion. So here's everything I just talked about for Lesson 8 in 1 slide. So you have confidence intervals and hypothesis tests for 1 sample proportion, 1 sample mean, and paired means. So this is really, I think this is pretty useful because it puts all the test statistic formulas and assumptions that you need to know just in one place to kind of consolidate it for you. All right, so in the population of Americans who drink coffee, the average daily consumption is 3 cups per day. A university wants to know if their students tend to drink more coffee than the national average. They ask a random sample of 50 students how many cups of coffee they drink each day, and found x bar equals 3.8 and s equals 1.5. Amount of coffee consumed is a quantitative variable, and we are given that the random sampling methods were employed. Because our sample size is greater than or equal to 30, we can approximate the sampling distribution using a t-distribution. So here I'm just asking you to calculate the test statistic given this data. All right, so we're going to go over this one now. So here's all the data that you have to plug in. I just kind of broke it down from the question. So we have our x bar, our mu, our standard deviation, and the sample size. So now we're just going to plug it into the test statistic formula. So 3.8 minus 3 divided by 1.5 over the square root of 50. And once we do that, we get 3.771 as our test statistic. Okay, on to lesson 9. So this one is 2 independent proportions and 2 independent means. So this is very similar to lesson 8 as before. I'll have the same chart at the end of the lesson, kind of going over everything and all the formulas that I went through. So 2 independent proportion tests are used to compare the proportions in 2 unrelated groups. So we call this the difference in proportions test. So you want to make sure that you have at least 10 successes and 10 failures for each group that you're testing. So both the first group and the second group. So for confidence intervals, you want to make sure that the assumptions are met, at least 10 successes and 10 failures for each group. And then the sampling distribution can be approximated using the normal distribution. So it would have a mean of p hat 1 minus p hat 2. And then your standard error, it's pretty lengthy, but I'll read it out. Square root of p1 times 1 minus p1 over n1. And then you add that to p2 times 1 minus p2 over n2. And once you add those two numbers together, you'll take the square root. And then after that, it's pretty much the same. So you have your confidence interval. You can calculate that by taking the difference between the p hats. That will be your sample statistic. Add and subtract that to the z star multiplier times your standard error. So for the 5-step hypothesis testing procedure, you're going to check your assumptions and write your hypotheses. So our assumptions here for the independent proportions is that there are at least 10 failures and 10 successes in each group. And just make sure that the two groups that you're comparing are independent of one another, that they're not paired at all. And then when you're calculating your test statistic, you want to make sure that you use a pooled proportion here. So a pooled proportion is calculated using the p hats for each group, and then the sample size for each group. And then once you get your pooled proportion, you can use that to calculate the standard error. And once you get your standard error, you can use that to calculate z. So it's a little lengthy as well. But once you calculate Z, your test statistic, you can determine your p-value and then decide between the null and alternative hypotheses and then make a real-world conclusion. All right, so moving on to two independent means. So for confidence intervals, if both sample sizes are at least 30, then the sampling distribution can be approximated using the t-distribution. So our confidence interval for two independent means is the differences between our x-bar, that's our sample statistic, plus or minus t-star times our standard error. Our standard error for the two independent means is S1 squared divided by N1 plus S2 squared divided by N2. Once you add those together, you can take the square root and that will give you your standard error. The degrees of freedom we use for two independent means, since we have two different sample sizes, we just take the smallest sample size and we use that to calculate our degrees of freedom. So from there, it's the same as before. So we'll just subtract 1 from the smallest sample size to get our degrees of freedom. So from there, we'll do the same thing as we did before. We're going to check our assumptions and write our hypotheses. Our assumptions is that both populations are greater than or equal to 30, and that are two groups that are independent of one another. Then we're going to calculate the test statistic for two independent means. Then we're going to plug that test statistic into the t-distribution in order to calculate the p-value. And then decide between the null and alternative hypotheses, and then state a real-world conclusion. Okay, so here's lesson 9 in one consolidated slide, just the assumptions that you need to make and the calculation of the test statistics for each group. So review 1, calculate the sample proportion for the group over 40 that steal. So I'm just asking you here to calculate the p-hat. All right, great. Our answer here is D. So really just going back to the basics a little, you want to make sure that you're still familiar with how to calculate proportions, just so that you don't get or overthink a question. And it's really just a pretty basic question to go over the answer that you definitely probably know how to calculate. So for an example here, calculate the proportion for over 40 that steal. So we just want to find where those two meet. So we want to find our group over 40 and those that steal out of the total number in that category of over 40. So we calculate 76 divided by 192 and we get 0.396 as our sample proportion here. So good job. So use these data to compute a 90% confidence interval for the difference in mean commute time between Atlanta and St. Louis. So I gave you your t-star here, it's 1.648. All right, so I'm going to go over this question now. So just finding all the numbers to plug in here. Oh, mean got a little cut off there. Um, but X bar 1 and X bar 2, you can find that the mean for group 1 and group 2, Atlanta and St. Louis. I just plug those numbers in there. And then add and subtract that to T star, which is 1.648 from the problem. And then really just plugging in the numbers into the standard error formula. So that consists of each standard deviation and then each sample size. Let's see here. All right, so our answer here is 7.41, or sorry, that's not our answer. So once we subtract X bar 1, X bar 2, we get 7.14 as our sample statistic, or our difference that we will add and subtract our margin of error from. Our margin of error is 1.85, and then once we add and subtract those out, we get an answer of 5.29 to 8.99. Okay, so moving into lesson 10, this is coming into more recent material. So the F distribution, you guys have already learned about the Z and the T distribution. And for the F distribution, we can compute F test statistics in order to determine a p-value for a one-way ANOVA. So for the F distribution, it has 2 degrees of freedom, so between groups and within groups. So the between groups, we call that the numerator. That degrees of freedom is calculated by taking k minus 1. So k is the number of groups, and we subtract 1 to get the between groups degrees of freedom. Within groups, also known as the denominator sometimes, that's calculated by our sample size minus k. So the sample size here is the total sample size with all groups combined, and then we subtract that by the number of groups, and we get the within groups degrees of freedom. So for hypothesis testing for one-way ANOVA, we have 3 assumptions that we want to check. We first want to check that our samples are independent. Second, we want to check that the response variable is approximately normally distributed, or that all sample sizes are at least 30. Then we want to just check that the population variances are equal across responses for the group level. So really just checking how the standard deviation matches up across all the group levels. And then when we're writing our hypotheses, we just say that mu1, for example, is equal to mu2 equals to mu3. And then for our alternative hypothesis, it's just that not all of our means, for example, are equal to one another. When we're calculating our test statistic, we can use Minitab in order to calculate that. There's no formula I can give you to do that. But in Minitab, it will provide 3 different degrees of freedom, and 2 of them you can use to actually look up your F test statistic. It'll give you between, within, and total. So total is just between and within added up to one another. Then once you have your test statistic, you can use the F distribution to determine the p-value, and the degrees of freedom will help you determine that as well when you're using the F distribution. Then decide whether to reject or fail to reject the null hypothesis, and finally state a real-world conclusion. If our numerator degrees of freedom for the F distribution is 4, then what is k? All right, great job, you guys. A is our answer here. So just going back to that formula, k is the number of our groups. The numerator degrees of freedom is equal to k minus 1. So if our numerator is equal to 4, we just have to find what minus 1 equals 4, and that is 5. So great job. Okay, on to lesson 11, just chi-square tests. So goodness of fit tests are conducted when there's a categorical variable with more than 2 levels. So if the expected counts are all at least 5, then we can use the chi-square test. But if any expected count is not at least 5, then we'll use a randomization test. So in a goodness of fit test, we can compare observed counts to expected counts. So the observed counts are the number of cases in the sample in each group. And then the expected counts are computed given that the null hypothesis is true. So this is the number that we would expect to see in each cell if the null hypothesis were actually true. So calculating expected counts, we can calculate that by taking the total sample size times the hypothesized proportion of whichever group you're calculating for. And then to calculate the chi-square test statistic, you can take the observed minus the expected value, square that, and then divide it by the expected value as well. Then you add up you do that for each cell, and then once you get each cell, you can add them up together, and that will give you your chi-square test statistic. So a chi-square distribution, similar to the T distribution and the F distribution, depends on degrees of freedom. So for a chi-square test, the degrees of freedom is equal to the number of groups minus 1. So to find the p-value, we find the area under the chi-square distribution to the right of our test statistic. So yes, this does mean that we always have a right-tailed test for chi-square tests. So again, going through the 5-step hypothesis testing procedure, we're going to check our assumptions and write our hypotheses, although here it's recommended to write the hypotheses first, and then just make sure that all your expected counts are at least 5. So you can check that by taking n times p. Then calculate your test statistics. So again, we went over the chi-square test statistic formula in the previous. Calculate it for each cell and then add up and find the sum of each cell to get the test statistics. Sorry, it's late. Step 3, determine the p-value. So construct a chi-square distribution with degrees of freedom. Your degrees of freedom is equal to the number of groups minus 1. And again, you're going to take a right-tailed test to determine your p-value. Then finally, it's the same procedure from here. Decide whether to reject or fail to reject the null hypothesis based on your alpha level. And then state a real-world conclusion, just addressing your original research question. So a chi-square test of independence is used to test for a relationship between two categorical variables. So you compute expected values for cells in a two-way contingency table under the assumption that the two variables are independent of one another. So for a chi-square test of independence, you will use the 5-step hypothesis testing procedure. So you're going to check your assumptions and write your hypotheses. Our assumptions here are that all expected counts are at least 5, and the samples are randomly drawn from the population. So our hypothesis here is that there is not a relationship between the two variables. We can say that they're independent of one another. And then the alternative hypothesis is that there is a relationship between the two variables, so they are dependent on one another. Then we calculate our test statistic. We calculate our expected cell value, and based on that, we can calculate our chi-square test statistic. Oh my goodness, sorry. Then we determine the p-value. So here in our chi-square distribution, our degrees of freedom is different based on the two-way contingency table that we used. So that's what you're going to use when you're determining your degrees of freedom. So you're going to take the number of rows in that contingency table and subtract 1. Then you're going to multiply that by the number of columns in that contingency table minus 1. And that will give you your degrees of freedom. And then again, you're just going to, from there, it's all the same. So you're going to take a right-tailed test to determine your p-value. Then decide whether to reject or fail to reject the null hypothesis. And then finally state a real-world conclusion. So moving on to relative risk. So if you remember, we just went over risk maybe like an hour ago. Risk is often used to describe the probability of an event occurring. So we went over that flu example, 45 out of 100 children getting the flu each year. Relative risk compares the risk of a particular outcome in two different groups. So it's the risk in group 1 compared to the risk in group 2. So suppose that the risk of a child getting the flu this year is 0.45 and the risk of an adult getting the flu this year is 0.10. What is the relative risk of children compared to adults? So here we would take the risk of a child getting the flu, which we'll call our group 1, so that's 0.45. And then we'll divide that by the risk of our second group, which is 0.10, and we get 4.5. So we can say that children are 4.5 times more likely than adults to get the flu this year. Okay, review 1. Calculate the degrees of freedom for the chi-square test of independence using the data on the right. Great, you guys got it. C is our answer here. Um, we want to make sure that you use the two-way contingency table method here. So that's really just calculating the number of rows. So here we have 2 rows, men and women. Subtract 1, and we get 1. Then we found a number of columns. We have 2 columns here, yes and no. We subtract 1, and we get 1. And then when we multiply those 2 numbers together, we get 1 as our degrees of freedom for the chi-square test of independence. So suppose 7% of teenage girls have asthma compared to 5% of teenage boys with asthma. Using the females as group 1, what is the relative risk for girls compared to boys? All right, great, you guys. 1.4 is our answer. Just going over group 1, 7% divided by our group 2 risk, which is 5%, and then we get 1.4. If you're wondering how we could just conclude this, we could say the risk of asthma is 1.4 times as great for teenage girls as it is for teenage boys. All right, so we're on to our last lesson, correlation, simple linear regression. You guys should be experts at this by now since you just most recently did it. So Pearson's R is a measure of correlation between 2 quantitative variables. So for samples, we use a symbol R, and for populations, we use a symbol rho. So there's 5 properties of Pearson's R. So it will range from -1 to +1. For a positive association, R is greater than 0, and for a negative association, R is less than 0. If there is no relationship between the 2 variables, that's when your R will be equal to 0. The closer R is to 0, the weaker the relationship is, and the closer your R is to positive or -1, the stronger the relationship is. So the sign of the correlation provides direction only. So whether your correlation is positive or negative does not have any say on whether it is weak or strong. Also, correlation is unit-free, and just remember that the correlation between y and x is equal to the correlation between x and y. Okay, so for hypothesis testing for correlations, you're going to want to check assumptions and write hypotheses. So in this case, we want to make sure that both variables are quantitative and that the relationship between x and y is linear. Just note that for your null hypothesis, you will always have your null hypothesis of your rho is equal to 0. That just states that there is no relationship between the 2 variables. Then you're going to calculate your test statistic. From there, you'll determine your p-value. Based on that p-value, you'll decide whether to reject or fail to reject the null hypothesis, and then state a real-world conclusion. So moving on to simple linear regression. So this is when you use one or more explanatory variables, or x variable, to predict one response variable, which is your y. So in here, we use slope and y-intercept. So our predicted value of y can be calculated using the y-intercept plus the slope times your x value. So slope can be positive or negative. It can just indicate the relationship between the 2 variables, whether they are positively related or negatively related to one another. And then the y-intercept is just the predicted value of y when your x is equal to 0. So there's 4 assumptions of simple linear regression. So first is linearity, so making sure that the relationship between y and x and y is linear. Second is independence of error, making sure that there's not a relationship between the residuals and the y variable. Third is normality of errors. So the residuals must be approximately normally distributed. So remember that bell-shaped curve. And finally, equal variances. So the variance of residuals is the same for all values of x. So thinking about standard deviation and the variance of data. So confidence interval for a slope. So this goes along with the same general formula we've had for confidence interval. But we use our sample slope as where we would normally have our sample statistic, plus or minus t star times the standard error of the sample slope. It's important to note that for the t star, that's the value you get from the t distribution, and we have a degrees of freedom of n minus 2 here for the confidence interval. Coefficient of determination is the amount of variation in the response variable that can be explained by the explanatory variable. It's denoted by r squared, and you can calculate the coefficient of determination by taking Pearson's r and multiplying it by itself, squaring it. So it's not too complex there. Just another thing to note is the influence that outliers can have. So most of the time an outlier will decrease the value of a correlation coefficient and it'll weaken the regression relationship. But in other cases, it actually may increase a correlation value and seem to improve regression between two variables that don't really have much relationship. So we call this an influential outlier. So in figure 1 and figure 2, it's the same data, except in figure 1 there is an outlier, and in figure 2 the outlier is removed. So you can see that the slope in figure 1 is much greater. It shows that there is a much more positive association between the two variables. When in figure 2, it really shows that there isn't much of a relationship between the two variables. So that's just how outliers can make it seem like there is a relationship between two variables, even if there really isn't. Extrapolation is when you use a regression equation to estimate the response of a data point when the value for its explanatory variable falls outside the range of the explanatory variables used to create the regression. So this kind of tests the trustworthiness of a regression model. So you want to make sure that you don't exploit the data too much so that it becomes untrustworthy. You want to make sure that you can use it to rely on it. You want to make sure you're using it inside the general scope of observations that fall within that data. So an example I like to use for this problem is if you have a simple linear regression model based on the heights of adults, and then you go and try to predict the height of a 3-year-old child through that regression model, you probably wouldn't get very accurate data because you base that model on the heights of adults and not the heights of children. Okay, so our first review for lesson 12. When x equals 0, what is the predicted value of y? All right, looks great. C is our answer here. 2 ways to figure this one out. 6.5 here, you can just automatically notice if you know the equation really well, you can say, oh, I know that 6.5 is the y-intercept because of the equation. Or if you had to plug in 0 for x, that works too. You can plug in 0 as your x, and you would automatically get 6.5 as your expected value of y. The correlation between quiz averages and final exam scores was r equals 0.60863. Calculate the coefficient of determination. Perfect, our answer here is C. So really all you need to do here is you take r and you multiply it by itself, you square it, and you should get 0.3704.